Hello, everyone. My name is Zhou from Avient Corporation. Thanks, Pinfa-NA for the invitation and the kind introduction. It is honor and privilege to give this webinar presentation today. I hope the presentation helped the audience gain a bit more understanding of the few commonly used fire tests in the plastic industry and material behavior each of these tests measures. In this webinar, we'll go over the following topics. First, to briefly go over terminology used for U.S. fire safety requirements. Then we'll go over 10 common material behavior in a fire and the related test methods, which include demonstration videos. We will also look at two case studies while talking about related material behavior in those case studies. And last, we'll briefly discuss about test correlation between different fire tests. Many fire safety requirements are commonly referred to as regulations, codes, standards, and specifications. These terms are sometimes used loosely or interchangeably, so I'd like to make some clarification here, and we'll use some US-related examples. Regulations are mandated by government and required by law. For example, FMV SS302 is the flammability of interior automotive material required by US federal government. Codes are typically from industry association, tells you what you needed to do. For example, codes from National Fire Protection Association, NFPA. In many cases, compliance with NFPA codes is voluntary. However, in some cases, federal or state agencies have incorporated wordings from NFPA codes into regulations. In these cases, compliance is mandatory. Standards provide how to execute codes and regulations, including test methods. For example, ASTM D2859 mesaminine peel test for evaluating flammability of carpet and rugs. Standards in US are typically developed by industry associations or nonprofit organizations, such as ASTM, UL, or NFPA. Specifications are outlines of the material requirements of specific company or product, are typically from OEM. For example, smoke toxicity specification from aerospace OEM. Guides are documents which explain concepts such as test methods or properties. It should be noted here that some documents are a combination of regulation and test methods. For example, California TB117 is the requirements and test procedures for testing the smolder resistance of material used in upholstered furniture. Although a fire is a complicated process, all fires have three basic elements in common that are described by fire triangle here: fuel, heat, and oxygen. Flame retardant works by interrupting the basic elements of fire. Plastic material have a few common reactions to a fire. As summarized on the right, there's a 10 material reaction or behavior in a fire. The first four, thermal degradation, ease of ignition, ease of extinction, dripping, and flaming droplet, are the most important behavior in the early stage of a fire. Flame spread, heat release rate are for a developing fire. Number 7, fire endurance, is related to a fully developed fire. The last three, smoke evolution, toxic gas evolution, and char formation, are the important material behavior in all stages of a fire. Standard test methods have been developed to characterizing this material reaction to a fire under different fire severity and application scenario. Since different combination of this material reaction, different scale of a fire, different material requirements are concerned in various applications, there are actually hundreds of different fire test methods that have been developed. We will go over only a few commonly used standard fire test methods in today's webinar. It's also noted that this material behavior in a fire are not independent behavior. They often affect each other in a fire process. This table provides a high-level overview of a few commonly used fire tests in North America for various applications, including the electrical applications, automotive, building construction, aerospace, and transportation applications, etc. It's certainly not a comprehensive list. The table is simply trying to connect each of these test methods to the related material behavior in a fire it measures. which is critical to FR requirement in the corresponding application each test is related to. As you see here, most of these test methods measures more than one material behavior in a fire. For example, UO94 vertical burn test measures the ease of ignition, ease of extinction, and also the dripping behavior. Pardon me using so many acronyms here to save space. The explanation of each of these acronyms is given at the footnote. It should be noted that there is no so-called best FR test in this test method, since they all application related with different fire severity, sample size, orientation, and a different way of measurement. So passing one test doesn't mean passing another. However, some correlations may be established between a certain lab skill test and a large fire test to provide a prediction capability of large fire test performance of material. We'll briefly discuss that close to the end of this presentation. Let's look at the first material behavior in a fire, thermal degradation. Thermal degradation is a critical process enabling ignition or continuous development of a typical fire involving plastics. Since the fuel of the fire comes from the thermal degradation or pyrolysis of plastic material. Thermogravimetric analysis, or TGA, is the most commonly used tool for characterizing thermal degradation of material. Only a few milligrams of sample is required for the test, and tests may be run with different gas atmosphere. Inert gas, such as nitrogen, is typically more appropriate atmosphere than air for study pyrolysis of polymer in a fire, because the flame above the burning solid material can consume a lot of oxygen nearby and rendering an oxygen deficient area right above decomposition zone of the material. TGA may be run either using a constant heating rate or isothermal conditions, that is, keep the temperature at a constant at an elevated temperature. Multiple pieces of information may be extracted from TGA result, such as on-site degradation temperature TD, or the temperature at the maximum weight loss rate TP, and temperature ranges for thermal degradation process, and the char yield at the end of the test. TGA can also be coupled with downstream and analytical tools such as GCMS or FTIR for composition analysis of gas products of pyrolysis process. Since it's readily available and requires only a very small amount of sample, TGA is a very useful tool for screening formulations to study their thermal degradation or for evaluating thermal stability of FR additives. An overlay chart of a separate TGA curve of two example polymers is shown on the right. Polyamide PAI with a highly aromatic backbone structure shows a much higher TP and TD than the polymethyl methacrylate PMMA as shown here. Ease of ignition. Ignition is the starting point of any fire process which requires all three fire elements. How readily will a material ignite? To what kind of ignition source? Is that a cigarette, overheating electrical device, or large open flame? There are two major types of ignition tests. Type 1 ignition tests measure on-site temperature or on-site time or critical heat flux for a material to reach ignition point under specific test conditions. Such tests including ASTM D1929 test, which measure ignition temperature of material with or without pellet flame. The surface temperature at ignition of thermoplastic material is generally constant and independent of heat flux, so T-ignition measured by ASTM D1929 represents a material property. The following table shows the flash ignition temperature measured with the pellet flame and self-ignition temperature measured without pellet flame, and the degradation temperature TD measured by TGA method for a few common polymers. As you may expect, there is correlation between the degradation temperature from TGA and ignition temperature, especially flash ignition temperatures. The audience may find out more details from the references listed here. Type 2 ignition tests are application focused. Type 2 ignition or flammability tests typically use a small flame or small heat source as ignition source, which is to simulate a specific application scenario. For instance, electrical heated wire in a glow wire test is used to test appliance, Cigarettes are used to test upholstered furniture, and a Bunsen burner is used in UO94 test for electronic applications. The most common ignition tests use Bunsen burners. The application-related ignition tests also typically measure more than one material behavior reactions to the fire. We'll take a look at UO94 test in more detail in the next couple of slides, as it is the most popular flammability test for plastic material. UO94 standard in fact include multiple test methods, of which the following three are more commonly used, namely horizontal burn test, vertical burn test, and 5VB and VA test. The test requirement following from less stringent to more stringent from left to right in terms of the fire severity and test criteria. You can see a comparison of the fire severity in terms of the flame power and flame exposure time of these three tests shown here. The 5VB and VA test has much more intense firepower and also longer exposure time compared to other two tests. UO94 test measures multiple material reactions to a fire, which include the rate of the burning in the horizontal burn test, and flame out time (FOT) and ability to resist a flaming droplet in the vertical burn test and 5VA and VB test. The 5VB and VA test also measure the burn-through resistance of the sample in the plaque sample geometry. Sample thickness strongly affects the result of UO94 tests. Generally speaking, the thinner the sample is, it is tougher to pass the specific test requirement. In case of the thin sample, such as a film, a modified method, UO94 VTM method, is used. This test is similar to the vertical burning test, except that material is wrapped around a mandrel before clamping to the stand, and the flame application time is also reduced. In this test, the flame is applied only for 3 seconds versus 10 seconds in regular vertical burn tests. This table shows the pass or fail criteria for V2, V1, and V0 rating per UO94 test standard. Pass or fail criteria requirement including the individual burn time or flame out time T1 and T2 after each flame application, and total flame out time of 5 bars T1 plus T2, and the individual glowing time T2 and T3 after the second flame applications, and a caution ignition due to the flaming droplet. This requirement changing from less stringent to more stringent in sequence of V2, V1, and V0. UO94 test with a specific performance target is a pass and fail test. We'll discuss about evaluating probability of a pass and fail test and why the sample condition prior to the test is important on a later slide. Let's take a look at a quick demonstration video of UO94 vertical burn test as a next. Testing of two different samples are shown here side by side. The sample on left is a PETG control sample without any FR additive. The one on right is non-halogenated flame retardant PETG sample. As you notice here, besides some flame off time difference between the two, the sample on left had a caution ignition due to the flaming droplet, while the one on right didn't. So the sample on left is rated as V2, the other one is V0. We'll look at a UO94 5V test, the most stringent test among all UO94 test methods. This table shows the pass and fail criteria for 5VB and VA ratings. Typically, a sample won't be tested for 5VB and VA unless it's already rated as a V0. In this test, two sample geometries, both vertically mounted flame bars and horizontally mounted plaque of the same formulation, should be tested. 5VB and 5VA have the same requirement in terms of the flaming and glowing combustion time and caution ignition requirement. The difference is that 5VA doesn't permit a burn through, while the 5VB does during the test of the plaque sample geometry. We'll take a look at a quick video demonstration of the UO94 5VA test as next. Here's the testing of two sample geometry of the same formulation as shown side by side. A vertically mounted flame bar on left and a horizontally mounted plaque on right. As you notice, the flame source used here is much more intense than the one used in the UO94 V0 test. There's 5 flame applications here. Number 3. Number 4. In this video, after the 5th flame application, the vertical flame bar quickly extinguished, and the plaque sample didn't develop or burn through either. So after the same result is achieved out of the 5 repeats of each sample geometry, the sample is rated as 5AA. Another application-related ignition test is IEC glow wire test. It measures the ease of ignition, ease of extinction, and the flaming droplet. Here we provide a list of definition of related flammability terms in IEC 60695 test. Glow wire ignition temperature, GWIT, is related to the ease of ignition. Glow wire flammability index, GWFI, is related to ease of extinction. Ignition of the tissue papers under the mounted sample due to the flaming droplet is also considered in the test. Glow wire ignition temperature is maximum temperature which does not cause the ignition while the glow wire is still in the contact with the specimen. Ignition here is defined as a flame that persists for longer than 5 seconds during the test. Now let's look at a short video demonstration how the GWIT is measured. This video demonstrating how GWIT is determined. 2 separate specimens of the same sample formulations were tested in the side-by-side videos here. The ignition did not occur at a glow wire tip temperature of 800 degrees C on the left, while it did at 825 Cs as shown in the video on the right. With the 3 repeat, the maximum test temperature, which does not cause ignition, is determined as 800 C, so GWIT per IEC definition is 825 degrees Celsius. In this method, it's typically easier to achieve extinction than to prevent ignition at the same test temperatures. As you noted from the video, the flame extinguishes as soon as the wire is removed from specimen in both temperature settings. With a further test at a higher glow wire temperature, the GWFI was determined as 900 degrees C for this sample. Ease of extinction. How easily will the fire go out? Ease of extinction is very closely linked with ease of ignition. It is often measured in terms of flame off time or extinguish time as a part of the flammability or ignition tests, such as UO94 tests and glow wire test, which we just talked about it. Limiting oxygen index or LOI test is specifically for measuring this material behavior in the fire. The test measures the lowest oxygen content for 3 minutes of the steady burning of a candle-like fire. This means a material with LOI less than 21% is very easy to burn. LOI measured per ASTM D2863 generally depends on the material composition only, hence can be regarded as a material property. A list of LOI numbers of common thermoplastic polymers are shown here. The higher LOI is, the easier the extinction occurs for a specific material. This table is a brief summary of a typical requirement of LOI sample dimensions and the quantity as needed, and what the test measures. Then we'll look at a short video of LOI test as next. In this video, LOI tests of 2 comparative samples are shown side by side. For the sample on the left, which is a halogenated FRPP sample, the oxygen content of the test atmosphere was set slightly above the LOI number of the sample. While for the sample on the right, which is a non-halogenated FRPP sample, the oxygen content was set slightly below the sample's LOI number. The sample on the left can sustain the burning, while the sample on the right, as you can see, is gradually extinguished within a minute. You also notice a good insulation char formed for the non-halogenated FRPP sample, but not as much as a char in the sample on the left. Drippings and flaming droplet. Dripping is a very common reaction of thermoplastic material in a fire. Dripping can be non-flaming or flaming. Flaming droplet can cause spread of ignition to surrounding areas. It's why UO94 vertical burn test, including caught ignition due to the flaming droplet, as one of the pass-or-fail criteria as shown here. V0 or V1 rating do not allow caught ignition due to flaming droplet, while V2 does. On the other hand, dripping is a mechanism to remove heat or material from the pyrolysis zone of burning sample, hence can result in extinction. Dripping without causing ignition of cotton is allowed for UO94 V0 rating, and in fact a contributing factor to favor extinction. If you recall the UO94 V0 test video we watched, the neat PETG control sample with V2 rating had a flaming droplets, while the non-halogenated FR-PETG sample with a V0 rating also had a dripping, but in form of non-flaming droplets. Dripping is also observed in other fire tests, such as ASTM E84 test, which is also favor extinction of the burning sample. Although the behavior of the flaming droplet could be a potential concern, it is not currently considered as test criteria to determine the flammability reading of the material in the ASTM E84 test. Case Study 1. Grenfell Tower Fire. This tragic fire accident happened about 4 years ago in London, resulting to 72 fatalities. Many things went wrong in this case, including the legal issues, and the public inquiry of the accident still ongoing in UK. However, just look at this group of pictures shown on the right, you can tell an extreme fast fire spread along the exterior wall of the building happened, which directly contributed to the disaster. The initial fire was reported to have started from a fridge fire in a fourth-floor apartment, broke out a window to ignite the facade system, after which it spread very rapidly upward along the outside of the building, then into almost all the other apartments. The exact mechanism of the fast fire spread is not fully understood yet, but the design and installation of the facade and its material selection have been identified to be responsible for the fast flame spread. If we look at the schematic shown on the left, the facade design of the Grenfell comprises an aluminum composite panel, so-called ACM panel, on the outside, and a polyisocyanate PIR foam behind, and also an air cavity between the ACM and PIR foam, which was intended for thermal insulation purpose. The ACM panel here is a sandwich panel made from a too-thin aluminum sheet and polyethylene core. First, from material selection perspective, both polyethylene core of the ACM and PIR foam are easily combustible material, especially polyethylene core. When it burns, it not only releases a lot of heat, it also generates flaming droplet, which was seen in the accident photos. Secondly, the cavity between the ACM and PIR foam act as a chimney, is likely have promoted such rapid flame spread in the accident. These factors are highlighted in the House paper in 2018 as a reference listed here. The original design considered a good aesthetics and thermal insulation aspect of the facade, but is a big failure in terms of the fire protection of the building. ACM panel has been clearly banned for use in a new high-rise building in UK since this accident, but that regulation should have happened earlier. Flame spread. From the Grenfell fire case study, we can appreciate the importance of understanding and evaluating flame spread and heat release of material in a building application. For a building assembly, for example facade, flame spread not only depends on the component material, but also the design and even installation method of assembly. For evaluation of flame propagation of the exterior wall system containing combustible material, a large-scale fire test of the mock-up assembly should be used. For example, in the NFPA 285 or BS 8414 test. This is a fire test for the assembly, not for components. We'll spend a little more time to introducing ASTM E84 test here, which is also called as Steiner-Turnell test, since it's the most popular test for building application in North America. It measures the relative surface burning behavior of a building component, such as wall cover or ceiling cover, instead of a whole assembly, It is often referred in the building code, such as International Building Code (IBC) code, with a Class A, B, or C rating for flammability requirement of the interior finish of the building. Such as class rating is based on the Flame Spreading Index (FSI) and the Smoke Development Index (SDI) result, which the test measures. We'll watch a short video demonstration in the next slide to show how E84 test is run, what the test measures, and the sample requirement, etc. It should be noted here the result of the E84 test often depends on the material thickness and the substrate to which the material is bonded to in the application. For example, if the facing material passed the Class A rating, it doesn't mean the laminated structure comprising the facing and the combustible substrate can pass the same rating. So the sample for E84 test should represent material configurations in the real application as much as possible.
Welcome to SGS's demonstration of the ASTM E84 Steiner Tunnel Chamber Standard Test Method for surface burning characteristics of building materials. SGS is proud to be home of the newest, state-of-the-art Steiner Tunnel Chamber in North America. Prior to testing, the test item is cut to size and mounted appropriately to mimic actual installation. The specimen is then placed in a conditioning room with regulated temperature and humidity settings. Once a constant weight is reached, the specimen is ready to test. The test specimen, measuring 24 inches wide by 24 feet long, is placed horizontally on the test chamber's inner ledges, facing down. Specimens that are not required to be mounted to a substrate are laid upon wire mesh and steel rods for support. Once the test materials are secured properly, the test chamber is closed with a watertight seal. The test material is then subjected to extreme gas flame exposure from 2 natural gas burners. A 3-inch opening near the end of the tunnel, as well as a regulated exhaust fan, allows air to be drawn through the tunnel at a steady rate, ensuring that the igniting flames are able to spread naturally across the face of the test specimen. During the test, a technician continually records flame advancement through the tunnel's observation windows, while the photometric instrumentation in the exhaust duct records the specimen's smoke developed. The 10-minute ASTM E84 test establishes the specimen's flame spread index and smoke developed are reported. During the test, the technician notes the time at which the test material ignites. The maximum flame spread distance is recorded, as well as the time at which maximum distance was reached. This determines the flame spread index. Flame spread index and smoke developed are reported, product classified accordingly. Any specimen that fails to meet these specifications is considered unrated. The test is concluded after a 10-minute flame exposure. SGS proudly invites you to witness this state-of-the-art test and view North America's newest ASTM E84 Steiner Tunnel Chamber at our Farmingdale, New York laboratory.
Number 6 material behavior in a fire is the heat release and heat release rate. How much is heat released and how quickly? Heat release rate of fire is highly correlated to how fast the fire propagates. Cone calorimeter test per ASTM E1354 standard is a bench scale test that is commonly used to quantify the heat release profile of a combustible material. Only a small size sample with a 4-inch by 4-inch dimension is needed and mounted in a horizontal orientation typically under a given heat flux from a cone-shaped heater in the test. The cone calorimeter test is a very useful test for studying material behavior in a fire because it provides multiple pieces of information simultaneously, including time to ignition, mass loss profile, heat release rate profile, and a smoke release profile, etc. The heat release measurement is based on the oxygen consumption during the burning process, which is based on the observation that the thermal energy produced by a fire of a combustible material is generally proportional to the amount of oxygen it consumes. The smoke release measurement is based on the light transmission measurement of the smoke collected in the exhaust duct during the test. A laser light source and a photodiode are used in the setup. Here let's look at a short video demonstration how the cone calorimeter test is performed. The sample shown here is a flame retardant composite sample. Did you see the spark igniter right above the sample? Ignited. It's a pretty intense fire. The example result of the heat release profile and the smoke release profile of this sample as function of time as shown on the right. In this case, a major peak with a couple of smaller shorter peaks are seen in the heat release profile. The smoke release rate curve follows a similar trend. Generally speaking, the time of the cone calorimeter test takes depends on the sample. It can vary from a couple of minutes for thin samples to more than 20 minutes for thicker combustible samples. You have to wait for at least 120 seconds after the flame has extinguished to ensure the reignition doesn't occur before ending the test. So watching the video of such a cone calorimeter test is very helpful. So it's not just getting the final result as a heat release curve or smoke release curve. You're watching this test, how the test is run, so actually can provide you a lot of other information which the result does not necessarily provide. Another test for measuring heat release of a fire is OSU heat release test per FAR 25.853, which is a test method invented by Ohio State University researchers in 1970s, later standardized as the ASTM E906 method, then adopted by Federal Aviation Administration FAA as a material flammability requirement for aerospace industry in mid-1980s. A sample of 6-inch by 6-inch size is vertically mounted in OSU test chamber and ignited using the radiating heat panel and 2 pilot flame, and the heat release rate of test material is continuously monitored for 5 minutes. An example result chart of OSU heat release test is shown on the right. It is pass or fail regulatory test for a heat release requirement of aircraft interior materials. The test samples need to achieve both integrated heat release in the first 2 minutes to be less than the 65 kilowatt minutes per square meter and peak heat release of less than 65 kilowatt per square meter in order to pass the test. So it's sometimes called as OSU 6565 test. Fire endurance. For a fully developed fire scenario, one of the concerns would be how rapidly the fire penetrates the wall, floor, or ceiling that separate the rooms. ASTM E119 test is used to determine the duration for which a building assembly is able to contain a fire, retain the structural integrity, or both during a predetermined fire exposure in the test. This is a large-scale test with the exposed area of the test assembly to the furnace measured as large as 10 foot wide and 10 foot high. During the E119 test, the temperature rise on the unexposed side of the assembly, which is the backside, are monitored at multiple locations, while the exposed side is subject to predetermined time versus temperature curve, which is shown on the chart here. The fire exposure stops when the average temperature rise of the unexposed side is more than 250 degrees Fahrenheit above its initial temperature. After the fire exposure, a whole stream test is also performed on the exposed side to see if the stream can penetrate the assembly. The rating is expressed as the hourly duration, matching the time the assembly can be tested up to per the condition of acceptance defined in the standard. A couple of takeaways here. First is a test for a building assembly system instead of a component test. Second, the hourly rating is not intended to be correlated to the time assembly will perform in a real fire because of the wide range of potential fire conditions. But it does provide a relative comparison between the product and assemblies if they all tested using the same test method. Case Study 2. Both airplane accidents cited here happened in 1973 and both involve a Boeing 707. Although there are other causes for these 2 accidents, the smoke behavior of the aircraft fire was found as a major contributing factor to the fatal result. An airplane is a confined space where the smoke once generated cannot be efficiently ventilated. Heavy smoke could be worse than the thermal effect of fire for the following two reasons. First, smoke can severely impair the vision of the victim or rescuer, which is optical effect. This is the case happened in the Pan American Flight 160, where the heavy smoke in the cockpit seriously impaired the pilot's vision, and the airplane crashed just short of the runway in the emergency landing. Second, the smoke can cause asphyxiation and poison of the passengers, which is a toxicity effect. This happened in the Varig Flight 860 accident, where the 117 passengers initially survived the crash landing in a field in an emergency landing attempt, but the majority of them unfortunately died to the toxic gas of the fire, did not have a chance to escape. These two accidents happened in 1973, caused further changes in regulations, design, and procedures for Boeing 707 and future airplanes. Smoke release. As just mentioned from case study 2, smoke release and related toxic gas evolution are two important material behavior in a fire, especially for a fire that happens in a confined space. The question we have for the smoke release are how much smoke is released and how quickly. The most of the smoke release test methods measure the amount of smoke based on the light obscuration effect. This is a very practical approach as it quantifies the reduced visibility due to the fire smoke. ASTM E662 test, also referred to as NBS smoke density chamber test, is such example. It is also the most commonly used test in the US for smoke release measurement. Other fire tests such as a cone colorimeter test and an ASTM E84 test also measure the light obscuration effect of a fire smoke, but the results there are calculated differently from that in the ASTM E662 test. In the NBS smoke density chamber test, a sample of approximately 3-inch by 3-inch size is vertically mounted in the chamber and exposed to a 25 kilowatt per square meter IR radiator and a 6 small flame burner if the test is run using a flaming mode. If the test is running using a non-flaming mode, only the IR radiator is used, no burner flames. A white light source and a photocell are used for measuring optical density of the smoke accumulated in the chamber. The equation shown on the left shows how the smoke density number ds, which is proportional to the optical density of the smoke, is calculated in the test. ds does not have any unit, just like optical density. Maximum smoke density dm of a couple of example polymers are shown in the table on the right. It should be noted that the smoke formation is not an inherent property of material because many other factors such as sample size, sample orientation, ventilation, heat flux all can affect the amount of smoke generated in the test. But the structure of a polymer does influence smoke formation tendency of the material. A couple of very simplified generalizations could be made as follows, but there are also exceptions. Aliphatic polymers such as a polyethylene or polypropylene has a less tendency to produce smoke than aromatic and polyenic polymers. Second, polymer with aromatic unit in the backbone such as a polycarbonate have a less tendency to produce smoke than a polymer with a pendant aromatic group such as a polystyrene or ABS. This is related to higher thermal stability of the former polymer type. Toxic gas evolution. The other major effect of fire smoke is toxicity effect. As mentioned, this is especially important for mass transportation application, such as airplane or rail cars, as they belong to confined space where the toxic gas cannot easily ventilate. The gas toxicity is related type of the toxic gas substance and their concentration in the smoke, which directly affects survival rate of the victim in case of onboard fire. The corresponding smoke toxicity test for the aerospace and railcar application in the US is a BSS 7239 test. In this test, 6 gas species, including the carbon monoxide, nitrogen oxide, including the nitrogen monoxide and nitrogen dioxide, and sulfur dioxide, HCl gas, HF, and HCN gas are measured. The smoke samples is typically collected during the NBS smoke density test at a 4 minutes point of that test. BSS 7239 method allows multiple gas detection methods depending on the gas species. For non-acid gases like CO, NOx, and SO2 gas, flue gas analyzer based on a non-dispersive IR or Draeger tube or FTIR can be used. For acid gases, Draeger tube and all FTIR technique are common. A wet chemistry method followed by ion chromatography can also be used for toxic gas detection, which is more tedious to run, but the result may be more reliable. Here we look at the Draeger tube method in a little more detail. The Draeger tube is also called a colorimetric chemical sensors. A Draeger tube is a glass tube filled with a chemical reagent and a filter layer that can react with a specific gas substances and turn color as a result of a chemical reaction. The substance conversion in the tube is proportional to the mass of the reacting gas. It is possible to indicate the substance conversion as a length of discoloration on the tube. So if a fixed volume of sample air or smoke flows through the tube, the concentration of the test substances can be directly read out as a length of discoloration on the tube. To pass the BSS 7239 test, the concentration of each of these 6 toxic gas substances has to be below their individual spec limit as shown here. Generally, based on the composition of the sample being tested, you may expect the result to some degree. For example, the nitrogen-containing polymer or additive in the formulation will likely generating HCN gas in their smoke sample. The advantage of Draeger tube method is its simplicity, as it doesn't require complex equipment, so it can be cost-effective if not many samples are to be tested. And also fast, because no user calibration is needed, and the result is immediately shown. The gas detection method using FTIR technique can also be very useful because it can provide a time evolution of multiple toxic gas simultaneously to study a fire process, and it could be cost-effective as well if a large number of the sample are to be analyzed. The last but not least material behavior in a fire is char formation. What is the effect of the formed char layer to a fire process? A char is formed at the interface of condensed phase and gas phase of a burning solid material, which can in turn affect the progress of a fire in terms of smoke release and heat release behavior. A intumescent material, when exposed to a fire, forms a formed char layer that isolates heat of the flame and gas phase from the underneath material. Meanwhile, the char may reduce the smoke release due to its barrier effect to the pyrolysis zone. So a good char layer formed in the burning process protects the unburned material underneath the char. A correlation between the heat release rates and char yield of a few thermoplast polymers is shown here. As you see, the high-performance polymers such as PESU, PEI, and PEK with a highly aromatic backbone structure show high char yields and very low average heat release rate. On the other side, polyolefins resins and acrylic resins with aliphatic hydrocarbon backbones burns very cleanly without much char formation in the fire test, but their average heat release rates are very high. The common test material for measuring char formation include TGA and microcombustion calorimeter test, MCC test. Both tests can measure the char yield using a teeny amount of sample. In general, the char yield from both TGA and MCC methods using inert gas atmosphere are comparable for many polymers. Examples of char yield of polycarbonate and the PEI, polyether imide, at the end of MCC test is shown in the photo here. In the cone calorimeter or horizontal burn or furnace exposure test, the char formed at the end of the test can also be evaluated quantitatively or qualitatively. First, the weight of the char can be calculated based on the mass loss result and the non-inorganic filler content of the formulation. Secondly, the height of the thickness of the char layer could be measured if the intumescent sample are tested. Example is shown in the photo on the upper right here. Thirdly, a char layer can also be qualitatively characterized in terms of the sturdiness or porosity of the char. Is that a thin, flaky char layer or the dense, uniform foam char layer? If the char easily flakes off, it typically doesn't protect the underneath material. We have introduced a few commonly used fire test methods in North America so far. For a formulator or fire scientist, some of these test methods are very useful as a material screening tool because they only require a small amount of sample and yet provide a reliable, useful information of the material behavior in the fire. As mentioned, the cone calorimeter is especially useful if it's available because multiple pieces of information its test result provide. UO94 is also commonly used because it's easy to set up and easy to run, relatively repeatable as well. Non-standard test for material screening was mentioned by Roger in the introduction webinar of this workshop in February. You may use extruded strand for a quick flammability test to compare or rank material behavior in terms of the ease of extinction or flame off time and smoke release behavior, etc. Caution should be taken regarding the safety and consistency to perform such a non-standard test. But if done properly, the non-standard test can provide a quick indication of some fire behavior of the material. So far, we have mentioned multiple standard fire test methods, small or large. Here are a couple of key questions for a formulator when designing a new flame retardant formulation. Question 1. What fire test is required to pass? And a related question, what material behavior that fire test measures? I hope the presentation we have gone through so far help you answer those two questions. Well, the question 3 is, can we correlate the result of two different fire test methods? In general, there is no good correlations between many commonly used fire test methods because there could be lots of difference in the testing conditions between those fire tests, such as fire load, sample size, sample orientation, and a pass and fail criteria, etc., especially if those tests were developed for different applications. Let's just look at the fire load difference here in the table on the upper right, which lists both fire load in terms of energy level of heat of flame source used and exposure time in each of these fire tests. They're vastly different. So with such big difference, it's not difficult to understand that passing one test doesn't mean passing another test. The second table on the lower right compares the heat flux per unit area the sample receives in each of these listed tests. This is an alternative way to compare the flame heat source used in the different fire tests. It's worth noting that there is some overlap in the heat flux level between the cone calorimeter test per ASTM E1354 and the standard internal test per ASTM E84, although the sample size requirement in those two tests are vastly different. A good correlation between the result of cone calorimeter test and that of E84 test has actually been demonstrated in some publications. There are generally two approaches for such correlation reported in the literatures. First, empirical correlations, where the result of the E84 test, such as flame spreading index, may be correlated to the heat release rate result of the cone calorimeter test. The empirical correlation approach, however, is limited to a specific material system that was studied. Second approach uses a generalized fire model, where the result of a cone calorimeter test may be used as the input of the model for predicting the flame spreading result of the E84 test. The audience may refer to the reference below to do your own further study if interested. All right, we come to the end of the webinar now. I would like to acknowledge the following people who have helped me with preparing this presentation. First, many thanks to my colleague at Avient Corporation, especially Stephanie Mims in Avient Fire Science Lab, who have helped with the test videos used in the presentation. And a big thank you to Tim, Roger, attendee, and the Pinfa North America Technical Committee for many helpful discussions. And thanks SGS North America for their ASTM E84 demonstration video. And thank you all for your attention. Now we give time back to the moderator. It's a time for your questions. Thank you.